All right, just an intro. The demand for critical minerals will increase over the next decade. Meanwhile, reliance on foreign imports is at an all-time high. On the left is the 2023 critical, mineral criticality assessment, and on the right shows supply by country over time, with 10 years in between each tick mark. So government and large corporations have recognized that there is a workforce shortage. Our country needs more geologists, mining engineers, chemists. But what if the engineers we have now could be 100 times more efficient or be in 100 places at once? That was the inspiration for creating the sensor. And I'll tell you all about how it works in the slides coming up. But first, a bit about myself. I'm an automation engineer, and in my day job, I build robots that build airplanes. And what does that mean? That means that I'm accustomed to solving problems through automation, and I work with hydraulics. And I knew that the toolbox of a chemical process controls engineer probably looked something like this. And just for fun, I put the approximate year that this sensor was invented below. On the left, temperature, that's a picture of an RTD, was invented roughly 1885. Pressure transducers, also very common for process control, 1940. This is a picture of an electromagnetic flow meter. There's different types of flow meter. That's really high tech, and I was surprised to learn that electromagnetic flow meters were invented approximately 1930. And on the far right is an industrialized pH probe. And I was surprised to learn in my research the way it's commonly done in chemical industrial process control. These systems are highly reliant on mathematical models. So the way it commonly works is a chemical engineer will work very hard to characterize a process and come up with a theoretical model that they believe is robust and repeatable. And these massive, expensive systems operate without direct control of chemical concentration, and instead rely on indirect sensing like pressure, temperature, and pH to maintain steady state operation. Chemical concentration is monitored periodically though, and the gold standard for metals analysis is ICP. ICP stands for inductively coupled plasma. And there's different types of it. This is an ICP OES machine on the right. And just to give everyone an idea, an ICP lab costs at least $120,000 per year to operate. So large companies like the one we saw on the previous slide might have a lab on site. Most people, like I'm sure everyone here, rely on dedicated analytical labs where you send samples, and you typically wait few business days to weeks to months to get the results back. I ran an ICP just before flying out, and with an expedite fee, they got me the results in 5 business days. So if ICP works so well and is very accurate for metals analysis, then why do we still use indirect sensing for process control? And the reason for that, the answer to that is there are different types of precision. While ICP will give you the best accuracy in terms of quantifying the metals, these sensors can provide precise timing. And this is just an arbitrary graph of an event. The thing to take note of is the x-axis in seconds. So this is the kind of thing that would be really difficult to capture if you're trying to measure a change in chemical concentration over a few seconds. Really difficult to do with ICP. But there's another time-tested technology that can measure chemical concentration pretty much instantly, and those are photochemicals. So you probably use something like this before to test the chlorine in your pool, and amateurs use it every day to test nitrate levels in aquariums. In fact, there's a whole world of chemical sensors out there, with hundreds being published every year. and thousands in the archive. And this is a picture of the front cover of American Chemical Society Sensors Journal. And a lot of the collaboration we've done is with these scientists working on novel chemicals for detection of all kinds of dissolved materials. So we created a system of interchangeable parts that's purpose is to functionalize liquid-liquid analytical procedures. And there are two categories of reagents that works with, colorimetric and fluorescent. So colorimetric reagents exhibit a change in absorbance. In other words, they exhibit a color change or a change in opacity with increasing or decreasing analyte concentration. Analyte is the material you're trying to measure. And there's fluorescent reagents where you shine usually an ultraviolet light source on the material, and it'll fluoresce or emit light at a different wavelength that the sensors instruments can pick up. So important note, the Hummingbird is not a sensor, it's a sensing platform. It's made up of several parts. These are the sensors themselves are rugged and clog resistant, and they connect to a nearby pumping and control box that contains precise pumps, reagents, and an industrial computer. And several sensors can be connected to the same control box. So on the left is just an exploded view of some of the parts that are in there to give you an idea. And on the right shows the mixing action. All of this mixing is actuated hydraulically, and what you're watching is the dispensation of a fluorescent reagent. In this case, the cone in this picture is made of clear acrylic, so you can see what's happening. But the sample is mixed with our acoustic mixing technology, imaged, and then ejected. So all chemical sensors have an effective range, and it's usually fairly small. The sensor we're looking at today works really good from like 0 to 20 ppm. But one feature of the sensor is that it can auto range. So for example, if you're trying to measure a dissolved copper sample with 5,000 ppm of copper in it, it might start with a high range measurement, and if it's towards the low end of the range, it'll manipulate the ratio of reagent to sample to effectively dilute the sample that comes in, reagent, and then scale the measurements by the dilution factor. This is the same kind of analytical procedures that they use for ICP lab. So now we have a sensing platform and we have a world of sensors, so we need a process for creating sensors. And the part we'll take a look at today is validation testing. So the case study we'll look at today is called DDTC, and it was originally published in 1956. It's been around a long time, and it's used in industry to measure copper content in food, rubber samples, and other industrial products. And it's also used every day by amateurs to test copper in saltwater aquariums. And I originally discovered it at my local pet store. So it's just cool to be able to find a sensor that's commercially available and functionalize it using this platform for an entirely different purpose. So how does it work? DDTC is a chelating agent, and it's preferential to copper. When copper forms a complex with DDTC, it turns opaque and absorbs light. But the uncomplexed DDTC is transparent. There's another ingredient to the reagent known as EDTA, because the material samples usually contain lots of different metals. So the EDTA's job is to bind to all of those metals, and EDTA complexes are transparent. So you end up with an optical signal that relates to copper concentration. And here's what it looks like. The sample on the left is 8 parts per million copper, 4 parts per million in the middle, and 0 parts per million on the right, and the solution will turn from yellow to tan to dark brown depending on how much copper is present. We were able to reference prior research to find lambda max. Lambda max is the peak absorption wavelength for a given material, And the orange graph here shows the absorption spectrum for copper DPTC. And the blue peak shows the light source that we use for this experiment. Lambda max is around 430, and our light source is 435. The closer you can match these numbers, you're creating a camera that essentially only sees copper DPTC. So how do we turn reagents into precise sensors? These are two tools of the trade. On the left-hand side is a 96-well plate, and it's essentially 96 little test tubes on a postcard-sized device. So you can do 96 experiments at once. And on the right is a 96-channel pipetter, and the purpose of that tool is to pipette all wells of one plate into all wells of another plate at the exact same time. And here's our experimental apparatus. It's a custom-built well plate reader on the left. I'll talk a bit about that. So we built a well plate reader that uses the exact same instrumentation as the Hummingbird sensor. And that's important because the research we do characterizes the device itself, the performance of the device itself as it's going to be used. And the fact that the 96 channel pipetter is injecting all 96 wells at once, it essentially simulates 96 Hummingbird instruments per experiment, so you get a lot of data quickly and you're able to test a lot of things. Here's a view of the apparatus illuminated on the left. On the left is a 3D model showing the pipettes extending past the light source into the well. So here's the scheme for how we perform the experiments. On the right is our reagent plate, and we test different formulas of the copper DDTC reagent. On the left is our simulated acid mine drainage plate, or SAMD plate for short. And we essentially pick up the reagent, slide the pipetter over, and inject the reagent into the wells while recording. So we capture the exact instant when the two fluids meet. And after we run an experiment, this is what a well plate might look like. In this experiment, we were testing a gradient of copper concentrations from 5 parts per million at the bottom to 120 parts per million at the top. And here's the plot we got from that experiment. It was a test of dynamic range. It shows that we were able to measure from roughly 0 to 80 parts per million effectively. Perhaps could go a little bit beyond there. And when we did the math on the worst case portion of this slope, we found that the system had a digital resolution of 0.1 parts per billion. But this was in perfectly clear sulfuric acid. And when the sensor is being used on samples that have higher turbidity or are naturally opaque, that performance parameter might degrade a bit, but this is a good starting point. And here's what the data set looks like per well. So at the beginning of the experiment, on the x-axis is time in seconds. At the beginning of the experiment, we have a very high light amplitude that's reaching the detector. You can see the turbulent period in the middle where the reagent is injected, and then the brightness after is lower. We measure the difference in starting transmittance over finishing transmittance. We get a differential signal. This is important because you can start with a sample that is opaque and measure the difference in opaqueness from before and after the reagent is injected. And just to get an idea, here's one frame from an experiment with 96 of these recordings. Most of the time spent in data analysis was waiting for Microsoft Excel to load because it was a huge data set. So next we wanted to test stability of the reagent in pH. And I just wanted to give you a view. This is our template for experiment specifications. On the top is a table specifying the reagent that's in each of the reagent plate wells with water at the bottom as a blank. And then on the bottom is our simulated acid mine drainage plate. This plate, all wells on the left half of the plate contain 20 parts per million copper, On the right-hand side of the plate, 10 parts per million copper, and there's a gradient of pHs from 4 pH to 3.5, 3, 2.5, 2, and down to 1.5 pH is where we characterized this reagent. And here's the plot we got from that experiment. There's actually 6 plots here, as you can see, and the lines are stacked so closely on top of each other, it kind of looks like one line. That's a very good thing. It shows that the characteristics of the reagent don't change much in varying pHs. So we wanted to test this reagent for a copper mining use case. So we received a sample of acid mine drainage from the Great Basin region, and we ran a metals analysis and found it contained 525 parts per million of copper. And these are the other metals that we tested for in this experiment. The graph shows the relative concentration with its heavy in magnesium and aluminum. So we designed a pretty complex experiment to test interference. So we want to know if other metals are present, does it trigger the sensor and cause a false reading where the sensor would think it's measuring copper, but it's actually being triggered by another metal. So I won't go through this all, I'll just show you 2 main points. The 2 objectives of the experiment are we wanted to determine which interferent metals cause a response by EDTC, and then quantify the effective concentration of EDTA for mitigating the crosstalk. Here's a quick look at the 12 plates that we ran for the experiment. Here's what the plates look like, just out of curiosity, and I'll make a couple of observations. On the right-hand side, you can see this band going from top to bottom, where all the wells are clear. We found out that's what happens when you add way too much EDTA. At some point, the EDTA just binds to all the metals there, and you get no response from EDTC. And we'll see that in the data. On the left side, all of those wells should be clear, but you can see towards the bottom left of each plate, those are the responses from some of the metals that do have an interference or interfere with EDTC. And as you can see from the left to the right side of the plate, we're increasing the EDTA concentration, and eventually that effect is mitigated. And here's the plot we got. One of the plots we got from this experiment shows responsivity to interferent metals versus EDTA concentration. So on the top is the responsivity to copper, and you can see that it's not affected much by the EDTA until you get to around 6,000 parts per million. And we found that the reagent formulations with 2,400 parts per million and 4,800 parts per million EDTA were the most effective. Nickel was the most significant interferent metal to the copper sensor, which was interesting. And here's the same data in a different type of plot. On the left-hand side, you can see nickel is still affecting the sensor, but this ended up being our winning formula, 4,800 parts per million EDTA. It shows that out of these metals, it really only responds to copper, which is great, because now we have a reagent that is selective for copper. We have an instrument that only sees copper EDTC. Next, we wanted to test the responsivity of the reagent to copper in the presence of other metals, which is a bit different, but basically does the sensor work the same way when other metals are present? It's the same thing. There's 8 plots here. The lines are stacked pretty closely on top of each other, which is a good sign. On the left-hand side is the 2,400 part per million formula. You can actually see nickel there towards the bottom. The graphs are sort of fanned out, but our 4,800 part per million formula shows pretty robust characteristics. All right, next we wanted to test this sensor on real acid mine drainage. So we performed a standard addition experiment, and basically we started with the raw acid mine drainage, and we added known quantities of copper to that mixture. And we got this plot here in the pink line, and we didn't know. Actually, when we ran this experiment, we didn't have the ICP results back yet, so we didn't know the starting value. But what we did was find the intersection of these 3 points on the trend line of our sensor characterization and calculated a starting part per million value of 455. And this is dissolved copper. The ICP analysis usually integrates all the total metals. So the fact that this measurement is a bit lower is consistent. And if you calculate the error from our ICP results to our calculated parts per million, it was 13%. A bit of a rough measurement, but the key thing here is that it's nearly instantaneous. All right, so we have all our characterization experimentation done, and the next thing to do was to install it in our Hummingbird platform and fire it up. So here's our test apparatus for sensor testing. And there's two important parts of this system. On the left is our addition column, where we can spike the circulating fluid with copper or any other analyte. There's a 2 horsepower pump. It actually ended up being way too much flow for a 1-inch pipe. And there were a lot of air bubbles in the line, but it was a good worst case test, and the sensor actually did pretty well. And on the right is a picture, close up of the sensor manifold. It's a clear acrylic block that lets us install sensors in there and observe them while they're working as well. Here's a plot we got from our experiments. The orange line shows the actual copper content. The system holds 3.7 liters, so we calculated the quantity of copper to add in order to reach 10, 20, 60 parts per million exactly. And the yellow arrows show the moment in time when that copper was added. The blue line shows the response of the sensor, and you can see that they track fairly well. Make note of the x-axis. The experiment was 20 minutes in duration. We received measurements every 20 seconds, but the dark blue line is a moving average of 3 points. And I believe the turbulence that we see here is because of the air bubbles.
5 minutes.
So what can this be used for? The original inspiration was refinery process control. Number 2, remote monitoring. There's, I believe, 500,000 inactive mines across America, which could potentially benefit from 24-hour-a-day, 7-day-a-week continuous monitoring. And the third is geological surveying. I got into a couple of examples of these. The first is engineered sorbent metering. So we've heard a lot about the addition of lime to settling ponds to precipitate metals. There's other additives that I've seen as well, like sodium carbonate. There's also some really advanced engineered sorbents I've learned about. Good example is resins. So there are resins out there that are selective for certain metals. There are resins that only bind to rare earth elements, for example. There's others for lithium that selectively bind to lithium. Those materials are more expensive than lime, so implementing them on a large scale is not feasible usually. But with this sensor, it can help bring those types of techniques into the realm of feasibility, because you install a sensor at the output. As soon as the metal concentration starts creeping up at the outflow, you add exactly the right amount of the engineered sorbent. The system stays in perfect balance, and you're only using the exact amount of sorbent that you need to bind the metals. Second technique, we coined passive mini refinement. So this was inspired by like oil and gas industry, where they pump, in a lot of cases, produced water out of a well, and that water needs to be treated before discharge, and it's dewatering is a very expensive process. So right now you can imagine a system where all the flow goes to one process, and the more water you produce, the more it costs. But what if you could have a sensor on the line that would measure the concentration of those contaminants, and just throw a diverting valve to move the material into one process or a different process, depending on how much cleaning it needs. You can potentially save a lot of energy. And this is another cool idea, adaptive drilling. During resource discovery, core drilling is common. And I think the way it's typically done is you'll plan a expedition ahead of time with certain locations you want to take the drills from, collect those samples, bring them back to the lab, analyze them, and repeat. So that cycle might take months or years. But what if, while you're drilling, you can install a monitor on the mud, it's called, which is the water and other detergents and stuff that come out of the ore. You can get rough measurements of chemical concentration as you're drilling. So when you find a deposit, you can adapt your drilling plan and try to target the deposits to find resources faster. That's all I got today. Invite you to stop by our booth. I've got samples of the sensor there. I'd love to hear from everybody who's interested.
We got a couple minutes for Dean if anybody has any questions.
So have you tested it beyond just copper, like for different metals or anything like that?
Yeah, we've done some testing. There are a number of metals in the R&D pipeline. This is brand new, so copper is our first product offering. It works well. So just to list some of the other metals, rare earth elements was actually our first project. We have sensors for terbium and neodymium. There's cobalt sensors, arsenic, and lithium. Yeah. And there's a long list of, there really is a whole world of these chemical sensors out there. So it's a brand new thing. And again, the idea is that it's a functionalization platform. So we want to, bring in some of the brightest minds who are working on these chemical sensors, and they'll just use this tool to implement it.
We have time for one more question.
You mentioned turbidity could introduce some error. Do you have a feel for how much? I don't know, as we saw photos and everything, there's probably no error we could quite turbid.
Yeah, so for the copper sensor that we looked at today, I could probably give you some quantitative estimates. I know that fluorescent sensors in general, turbidity affects them, but the rare earth element one. But the copper sensor is pretty robust. I mean, the light source that's in the sensor is very powerful. So the system essentially just scales the light source up until it gets a signal, and then you measure the difference before and after when the rate is introduced. So, I mean, you might see the sensors will be rated for 5% error, and then there might be a chart that shows turbidity versus error, and as you move up, the error bars will grow.
Cool.
Thank you, Dean.